Welcome back. In this video, we're going to take what we learned last time about a hypothetical endurance strength, which is a material property, and we're going to figure out how to take that value that was estimated on a very specific experiment and manipulate the numbers to be something more similar to a realistic case of what we should expect to see in our part. So the way we do that is called Marin Factors, and we're going to be setting up and figuring out how to define these Marin Factors. So the overall approach looks like this, that the actual endurance limit for our material in our part is a product of a whole bunch of factors times the hypothetical endurance limit. So in this class, we're mostly going to be using the first three factors, but there are many other factors that we could group in here. And so the first three factors, these Ka, Kb, and Kc, these are all Marin factors. And Marin factors are named after Alan Marin, which is in the 1900s, and he came up with these. And there are ways to correlate the actual experimental stress found with the hypothetical R.R. Morse test stand. So the first factor we'll look at is a surface factor, Ka. The surface factor is a way to account for the fact that the R.R. Morse test stand test specimen was ground and smooth, but more than likely our situation is not going to be ground and smooth. So the way we calculate Ka is like this. Ka equals a factor alpha times the ultimate strength and tension raised to the factor of B, where these values of A and B come from a table. And in your textbook, you can find this table, or part of this table is 6.2. It looks like this. So using this table, we can figure out what our ultimate strength of our property ought to be. Say 120 kpsi would be the ultimate strength. Then our Ka would be A. Let's choose a finish. Let's say it's ground. We'd have 1.34 multiplied times whatever our ultimate strength is. I think I said 120 kpsi as an example. And all of that raised to the B, which for ground would be this, negative 0.085. This results, using this example, as a Ka Marin factor of 0.89. So this is a great example in the sense that we will often calculate Marin factors as less than 1. And so all of our Marin factors multiplied times our hypothetical endurance strength will have the overall effect of reducing our actual endurance strength. So the hypothetical will be higher. Our actual endurance strength is going to be lower. In this sense, Ka takes about 10% off the top. The next Marin factor we're going to look at is the size factor, Kb. The size factor accounts for the fact that our test specimen in the R.R. Morse test stand was one exact size, and it depends on the thickness of the part to how well that part's going to carry it. So the size factor depends a bit on how it's loaded and a bit on how similar it is to the test specimen size. So if we have a part like the test specimen, which is rotating, and also it's in bending or torsion, then we define Kb like this. So for a rotating part in bending or torsion, the Kb is based on the diameter of our part that we're discussing. So if it's a round part, the diameter is pretty straightforward. So if it's round and solid, we take the diameter and we either divide by 0.3 and raise it to negative 0.107 for inches, And you can see the same thing for the metric scale on the right. Or if we have a larger diameter, then we can just use this form of the equation, 0.91 times the diameter raised to the negative 0.157. So what these are basically line fits to experimental data for solid round shafts. If we have a rotating shaft, but it's only under axial stress, then the size of the part doesn't make any difference. And this is because stress is equally distributed for axial loading. So the size factor doesn't make a difference. So what if our part is not rotating, or it's hollow and round? Well, then we need to use what's called the equivalent diameter. The equivalent diameter is basically the diameter of a circle that has 90% of the area of R shape. And there are several of these already figured out. So for example, a hollow shaft has an equivalent diameter of 0.37 times the original diameter, or the outside diameter. For a rectangular piece, this could be rotating or not, the equivalent diameter is 0.808 height times base, the square root of that. And we can find a lot more in the tables. It's table 6.3. So that is our KB size factor. Next is the load factor, KC. The load factor accounts for the fact that our test specimen in the RR Moore was under pure bending, but more than likely our situation is not. So if we are in bending, then KC equals 1, because the RR Moore test stand specimen was in bending. If we are in axial loading, then KC equals 0.85. It reduces the endurance strength again. And if we are in pure torsion, then KC equals 0.58. Finally, the last couple of factors that we won't be looking at as detail is KD, which is a temperature factor, KE, which is a reliability factor, and this general KF, which is not to be confused with the KF that we'll use later. This is just a miscellaneous factor. So these we won't use as much in this class. You can look through the book to see how they're defined. KF, or the temperature factor, often comes into play if we're dealing in unusual temperature regions. The reliability factor accounts for the fact that we may have there's an uncertainty according to the tests in the RR Moore test stand, and they're calculated at a certain % confidence level, and we may want to be more or less confident than that. And the miscellaneous factor accounts for other miscellaneous things. The only thing I want to note, and we haven't talked about it yet, but I'll talk about it in the next video, that we will have Kf as a stress concentration factor. And it is applied to stress, not to the endurance strength. So now let's see how we can put all these together and come up with an actual endurance strength. So let's do an example. Say, for example, we've got a round shaft that at the spot we care about has a diameter of 35 millimeters. It is made from 1020 cold drawn steel, which we can find the properties in the back. It's under some bending moment. The value isn't important to us at the moment. But that's the only type of loading that it is under. What is the actual endurance strength? Well, we can start off with what is the hypothetical endurance strength. So recall that for steel, hypothetical endurance strength is around 50% of the ultimate strength, as long as we're as long as we're not a very high strength steel. So the ultimate strength in tension of the 1020 cold drawn steel is 470 megapascals, and its yield strength is 390 megapascals. So this works well within our 50% of the ultimate strength range. So our hypothetical endurance strength, to start off with, is 235 megapascals. Now, to find our actual endurance strength, we need to compare it to, we need to use the Marin factors. So the actual endurance strength equals Ka, Kb, and Kc, and we'll just ignore Kd, Ke, and Kf, we'll call them 1 for now, times the hypothetical endurance strength. So now we just need to calculate what those Ka are. So for the surface, well, this was a round shaft, which means most likely, unless it was forged, it was machined. So we can use the tables in Chapter 6 to tell us what should be the A's and B's for a machined surface. So if we go back to that table, machine or cold drawn, our A, will be 4.51, and the exponent will be negative 2.65. Therefore, our Ka, which equals A times the ultimate strength and tension raised to the B, is 4.51 multiplied times that ultimate strength that we had, 470, raised to the B, negative 0.265. This gives us a Ka of 0.88. Now we need to account for the fact that the size of our shaft is not necessarily the same size as the test specimen. This is the size factor Kb. So recall the size factor Kb is based on the diameter. So this is a round shaft, a solid round shaft that is rotating. So therefore, we can use the regular formation of D. So Kb equals 1.24 times the diameter raised to the negative 0.107. If we put in our diameter, which recall was 35 millimeters, this gives us a value of Kb equal to 0.85. Now finally, we're going to look at the loading factor, Kc. Recall that our test specimen was in pure bending and our situation is in pure bending. So we're in the nice situation where Kc equals 1. So putting this all together, our actual endurance strength that we're going to compare the stress values to is Ka, which was 0.88, multiplied times Kb, 0.85, multiplied times Kc, which is 1, and the hypothetical endurance strength, which was 235 megapascals. When you do that multiplication, you come up with an actual endurance strength of 176 megapascals. So a good bit less than the hypothetical one that we started with. And from here on out, we'll compare the stress values and our Goodman equation to this endurance strength, which is modified to meet our actual situation. So next time, we'll talk about stress concentration factors, Kf. Until next time.